So here I'm going to draw one. So I have dark matter, I have ordinary matter, the gas, I have photon, the light, I have neutrinos, I have gravity waves. The gravity waves interact so weakly they just fly out at the speed of light. Neutrinos mostly go out near the speed of light, but the others don't go out so fast. You'll see what happens is there's a little bit of dark matter. A little bit of the dark matter is leaking out. It has to be cold, so most of it stays there. But it's just a tail of high energy particles that kind of leak out. But the matter and the radiation are tightly coupled, and so they blow out just the way the sun does. Okay, I'll finish up. I just love this part. So I have to. So I've gone out to 3/10 of a million years, and you begin to see the matter and radiation are beginning to separate. Right? Atoms are just barely beginning to form. If I go out to this time period, they've actually separated. The matter is starting to fall back into the dark well produced by the dark matter, and the baryons are moving into the dark matter, the gas is, and the radiation's beginning to stream out. And those things I see these particular shells out there. That's why, if you notice that picture, there was a certain angular scale picked out. The 1 degree angular scale was picked out because that's the size of this, the 150 megaparsecs, or 500 1,000 light year kind of scale size. The neutrinos flow out. If I let it run a little further, you'll see that most of the ordinary matter comes back into where the dark matter is, but there's a little bump left out here called the baryon oscillation peak. There's a little bump out at a few percent. So around a big cluster of galaxies, there should be a few galaxies that are out there at 450 megaparsecs, 450 kilolight years, a million light years, million. And you can look for those, and they have just been seen recently, the last couple of years. So there's evidence for this existing. But it also tells you the flatness of the universe, because you have the sound horizon. You know how big these are. You know how far away they are. If the universe is Euclidean, you have side, 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 so you know all the angles. If the universe is curved like the surface of the Earth, things converge, and therefore, when you extrapolate back, you project to bigger angles. And when it's a closed universe, like an open universe like a funnel, the things converge. And so when you extrapolate back, you get smaller angles. And so you can just compare the patterns on the map you saw with the patterns you have here, and you know what the angular size is, and they tell you the universe is flat. And you can do this in many ways. And so I have just 2 or 3 more slides, then I'll finish up. So you can do this in many ways. You compare the spectrum you would get, and if the movie runs, as you run the movie and change the curvature of the universe, you see this moves right or left. So if you do the angular power spectrum of the map and compare that to what you get, you can immediately tell that the universe is flat to better than 1%. That is, the radius of curvature is such that it must be 100 times the visible universe, right? Now you can also compare changing the curvature, changing the amount of dark energy, changing the number of ordinary matter, changing the amount of dark matter, looking at the heights of the peaks, the relative heights of the first and second peaks and so forth. You can tell what successes are. So we can get the numbers on that the universe has got 4% ordinary matter, it's got 23% dark matter, it's got 70% dark energy. We can do it by just looking at this power spectrum. So we're in a great situation of knowing these parameters in 2003 to that level. And by the time you get to 2006, you've got another factor of 2. And by the time we get to some later in 2008, we'll probably gain another factor of 2. We're getting to very great precision in knowing what the expansion rate of the universe, what the lifetime of the universe is, what the various functions are. We're really doing what I would consider, we're ready to start engineering the universe. So we've made tremendous progress. We're comparing the fingerprint of the universe to our file of fingerprints, and we're beginning to learn what the universe is. So we've got to figure it out. And this is what the South Pole looks like now compared to what I showed you earlier. And we're in the middle of our revolution. So I'll stop and answer questions now because I'm running over a bit. But